Welcome to the session. Greeting of the day. In today's class, we are going to talk about the types of thermography. Thermography is one of the non-destructive testing method that we have derived from the topmost 8 usages. See, here we have talked about these 8 types of NDT methods. Accordingly, the visual testing, liquid penetrant inspections, matic particle testings, then eddy current, radiography, ultrasonic, acoustic emission, and our interest of topic today is infrared thermography. Here, out of all these 8, infrared is also one of the type in NDT techniques. On that we are going to see one by one. In the previous lecture, we have divided such a classification towards the infrared thermography. See, infrared thermography is divided into active and passive modes. Active and passive modes. On that active is divided once again into internal and external. This internal is subdivided into video thermography. On that video, we have a burst mode and lock-in mode. Similarly, on the external mode, also we have a lock-in mode and pulsed mode. So these are the various classifications we have listed out in the previous class regarding the infrared thermography, which is also one of the non-contact method on the non-destructive testing. We know the meaning of non-destructive. We are not going to break the sample. We are going to pass any source of rays like radiography, magnetic particles. On that list, infrared also one of the category. In the previous class, we have also seen the spectrum where this infrared is falling down from the cosmic rays or X-rays to the radio zones from the left end to the right end we have seen. Now we enter into these types of active and passive one by one we will cover. Active thermography. This active thermography is an energy source is required to do this exercise of active thermography. Anyhow, we need some source of energy. We are trying to give a source. We'll see what it is. The energy source is required to produce a thermal contrast between a specimen and the background. First, we want to know, we are going to do some inspection on the surfaces. Surfaces may be a black color, and also the specimen where we are kept on the table or on the surface or on the land. Let us assume that it's both in the black color. We will be confused. Therefore, there should be some contrast between the specimen and the background what we are using. So the source of energy will give some contrast informations. When the same energy is falling on the specimen, it is going to reflect. When the same of energy is falling on the maybe any light sources or energy sources falling on the sand, it is going to absorb. So there will be some differences. So in this active approach, the active approach is adopted in many cases given that the inspected parts are usually in equilibrium with the surroundings. To be equal, we should not be deviate from other parameters. For example, specimen with the internal flaws. So this is our interest. We have to do inspection to find a crack over the specimen. So here maybe a specimen is available, and somewhere here the defects are there. This we have to find somewhere the light source or any you have to infrared energy sources or flashlights are passed over there, and then when it is reflected, we are going to observe by using a camera setup. So this is what thermographic camera methods. That's why I have written here thermographic camera. And that I have taken as a number 1 as an active method. So this active method is nothing but this method. So we are here. So this active method we have seen this method. The energy source in active thermography. A wide variety of energy source can be used to introduce a thermal contrast between the defective and the non-defective methods. What are the methods? If there is no contrast, we are not possible to identify the defects or discontinuities, and the energy will be wasted. Therefore, uh, we need to know go for some contrast that is given by two types of energies. The two types of energy is given as external energy or maybe the internal energy. We will see one by one these things. We will take external energy or internal energy. We will see. Out of all these things, somehow a common source of energy is there. The energy is delivered in the thermographic methods. Energy delivered, what are they? Energy is delivered to the source and then propagated through the material until it encounters a flaw. See, we have a specimen here. We have a specimen, and I'm sending the energy here. It keeps on moving, keeps on moving, keeps on moving until it's finding some type of cracks here. It's something defects here. Then if it is defect is falling down, it falls on the defect. It encounters by the flaw and it is wanted to reflect here. So we will have some cameras and we will detect those camera methods. So what is this energy? What we are sending here? What is this energy source? So what is that written here? Number one, photographic flashes, or number two, halogen lamps. It is nothing but a light source we are sending. A bright light source or concentrated beam of lights like a laser light beam we are sending over there, which is going to travel and it encounters on the flaw and it reflects, and then we are going to capture through a camera. A simple method. See, for heat pulsed stimulations. So number one, photographic flashes are for pulsed stimulation. Keep on by every seconds 5 pulses, every 10 seconds 2 3 pulses. It is manually we can fix and we can do. And one more thing is a halogen lamp. This we have here. After attaining certain heat, it will be off, return back to the off condition. So after getting down to those temperature, it again ons the switch. That is a halogen lamp we have come across this in our life factors. See? For that only it is mentioned as a periodic heating. So it is a pulsed heating method. This is a periodic heating method. Pulsed heating method is nothing but a photographic flash, and second one halogen for the periodic heating process. Now the source of energy is okay. We are releasing some source of energy is a flashlight which is going to fall. This flashlight has to travel through the specimen and it encounters and it comes back. When it comes back, that we are going to take method we have seen in the first one, active methods. On the active, we are having some external, internal. In the external, we have another two that is nothing but a pulsed and lock-in. So that is how we have divided. You see, one more time we will go there. Infrared thermography. On that I have active mode, passive mode. These are all type of inspection methods, not a source of releasing of energy. Source of releasing of energy is two methods. One is a halogen and one is a pulse methods, photographic method. So energy is released. It is going to fall on the specimen. How it is inspected when it is coming back, how I am taking. That is the idea here. When it's coming back, I'm using some active methods or it's a passive methods. So on that maybe in the active we have internal, external. So that all again subdivided. So as of now I have taken in this classification on the active method I have taken the external excitations. On that we are going to see about pulse thermography and lock-in thermography. So this is how this we are going to see this one, and we are going to see now. That is what. So the on the active thermography, we are again dividing in this external method into pulsed thermography, and one more is the lock-in thermography. Number one, as pulsed thermography I have taken. See, in pulsed thermography, generally we are giving some names or splitting. The specimen surface is submitted to a heat pulse using a heat power sources such as here it is itself easily understood, heat power sources. So that is nothing but a photographic source or maybe the halogen sources. So anything we are using, that energy is released and it is concentrated on a point of contact where our interest. I am assuming that here may be the defect. Then I am concentrating that flash beams, photographic flashes or halogen flash beams towards that point, and it is going to reflect back. See? High power source such as photographic flashes, or maybe in the pulsed method, heat pulse method. Therefore, there will be a certainly on and off methods we are using. A pulse, we know 1 by 1 hour for every 10 seconds, this many pulses, this many supply of flashes to be there. We are just intensifying process we are doing. On off method we are doing can be called. So it means on off methods can be called as a combination of several periodic waves at a different frequencies, amplitudes. Maybe a periodic, maybe a heat pulses. Any methods we can call. Generally, I am calling this as a heat power sources. So it is released. So see here in the picture, we will go for the second image. Here it will be larger. So you see here in the picture, here it is mentioned it is a flash lamp. So here it is a flash lamp. I am using two flash lamps here. So you know, two flash lamps here, and one more is a flash lamp. So here see, it's a small diagram is given, a pulse method. Small diagram is given, a pulse method. 8 pulse, a square one or maybe a peak one, whatever it is. So it is falling over the specimen. Specimen is here. We are sending a heat flash. It is falling over the specimen, and it can able to travel. So after that, it is falling on the defect and it is reflecting back. That infrared wave pattern, heat source is coming out in that wave. We have seen normally the 10 to the power of 2 micrometers. So in that range, and it is coming out. I have a camera here. Right, camera have a cover to protect the heat. Otherwise, it may damage and not work. Out of waters will come. Therefore, those things we have seen in the introduction class. How the infrared cameras are protected with the cover. So we have here infrared cameras which observes here. So this is the wavelength. Observes there, and it is a synchronized station because for every second it is giving you some data. Every microseconds, every pulse it is giving you data. So it has to be connected, and we have to plot some 3D graph where it is available on the x direction, on the y direction, and is that how where it is. We are not seeing, we are not scanning. It's not X-ray. We are not using magnetic field. We are not using any liquid particle inspection. It is such a type of wave understanding. It is such a type of wave understanding. So we are sending some heat sources of flash lamps, getting in, coming back. That we are observing to the infrared cameras, and the data plotted is 3D format and analyzing on the computer. See there? See, it is synchronizing data, and it is PC control the image processing in the 3D formats. That's what it also written here. Two photographic flashes, one at the top, one at the bottom, or maybe at the two sides, are used to heat up the specimen surface. After that, the thermal changes are recorded with the infrared camera. So here because of heat, flash lamps or halogens or generally it is a heating element. Wherever the light source is there is a heat. So that the thermal changes are recorded. Infrared camera to proper imaging of these particular defects to be done. For this proper imaging means it's a 3D where it is on x direction how much it should move, y direction how much it should move. So we want to analyze each and every point of heat source where it is. Where is the high heat? There is a defect. So the synchronizing unit is needed to control time between the launch of thermal pulse and the recording of the infrared camera. So in the pulse it is a second of time. It happens in a pulse or heat sources comes in a second of waveform. The time to be synchronized properly, where the flash lamp is initiated, when it comes back, and it is recorded on the infrared camera. So these two, when it is flashes, when it is recorded. So both should be synchronized. So these things are to be done by the synchronizing unit. The data is stored as a 3D matrix. It means nothing but x, y, z axes. Maybe it is because of subsurface defect. We are not having any other sources. Other methods we have seen remaining 7 types of NDT types. So data is stored as a 3D matrix where x and y are spatial coordinates and t is the time. Directly from IR camera data, the exact location of the particular defect inside the specimen is identified. You see the inside the specimen. Because we are understanding it's a subsurface that we are pausing to do. See, advantages. A pulse thermography is a fast, easy to deploy. Yes, we have two flashlights and a camera, and then synchronizing it, it is connected to the computer. And digitally it can be progressed, and with the image we can able to see in the 3D image where the defects are available, or maybe multiple colors, how far the waves are comes out. So therefore it is a faster one. Its experiment time varies from few seconds for high conductivity and a few minutes for the low conductivity materials. So it depends. A high conductive material, heat source easily absorbs, easily goes in, reaches the defect, reaches the discontinuity and comes back. Distribution of heat we are understanding. Maybe if it is low conducting, slowly the heat travels, split out and reaches the defect and it spreads. And that we are going to capture in multi-form of IR cameras. So it is having a very wide range of applications in terms of materials physical property. Maybe a low conducting material or high conducting material. It can possible, but it takes some time. That's what our understanding. Since the heat pulse can be seen as a set of several periodic thermal waves launched at once at several data points, amplitude or phase can be extracted from a single experiment. So when the heat is introduced at a point, it gives multiple data points. Multiple means the amplitude will be higher at the high temperatures, amplitude will be lower at lower temperature where it is distributed on the sample. So those data points have to be synchronized and can be extracted in many results. That is not our advantage, not at the specific point. Near zones also we can elaborate and we can able to see. Next point. The aperture thermography is very sensitive to voids or inclusions or cracks in the material. It can able to detect multiple discontinuities on the weld joints. We have seen earlier types of welding defects, or maybe types of casting defects. On that only these voids and inclusions are there. And our NDT also mostly useful for this type of industrial experiments. So there where it is voids and inclusions are easily identifiable. Some disadvantages. The data processing of a pulse thermography technique is complex as compared to the lock-in. So the lock-in method we have not seen. We have to see that. See, the data processing of a pulse thermography technique is very complex because this 3D image we are doing, which we are not doing in the lock-in methods, a concentrated method that we will see. See, therefore the result is affected by non-uniform heating. Anything where the heating is involved, it is going to observe because it is distributed all zone excited active methods. A pulse method only we are using, but it is external all zones we are using. It will be the uniform heating or non-uniform heating. Wherever the heat source is distributed on the surfaces from hot zone to the lower zone, it is going to give the result. So it may be a uniform or non-uniform. Anyhow, the camera goes to detect all the zones. So it is a non-uniform heating because it gives a result. That is a disadvantage I'm saying. It gives a result even if it is a non-uniform heating, even if it is a MCFT, any variations in the heating or environmental reflections also, because it immediately conduction convections are happens there on the specimen. All these things are able to affect our readings. Within a seconds we have to take solutions or take the exact contrast values through the synchronizing forms. Otherwise the environmental reflections will cool down the samples. The heat what it is included there will not be successfully taken out for our reading purposes. So those also definitely are the surface geometric treatments even though. So these are the various advantages and disadvantages of our pulse thermography, what we have seen in the external mode and which was already available in the active modes. See, as of now, we have covered in this lecture, and we have started with We have started with the infrared thermography introducing, and the types of active and passives are there. On the active methods, we have taken the external excitation method. On the external excitation method, we have covered this pulsed thermograph. For infrared, active, external, pulse method we have covered. And again, here we have to cover again this internal and vibrothermographies, and in the external also we have to cover the lock-in process. So that is what our next topic. See, it is now what our next topic, lock-in thermography, we have to do. The remaining part of the subjects we'll see you in the next session. Thank you.